So we define what is a measurable function. So we continue with the properties of the measurable function. So here is a proposition. So XS measurable space, F real valued measurable function on X, then mod F is measurable. So proof. So if let alpha belong to R, so we have to look at set of all X in X such that mod Fx is less than alpha, and that's equal to set of all X in X such that Fx is bigger than minus alpha intersection set of all X in X, Fx is less than alpha if alpha is greater than 0. Okay, and therefore this belongs to S because F is measurable. And if alpha is less than or equal to 0, then this set is empty, and therefore you have that. So therefore mod F is measurable. Remark, I leave it as an exercise for you to check. Converse not true. You can easily construct a counter example, so we will leave it at that. Now corollary, XS measurable space, F and G measurable real valued functions. Then max of Fg, min of Fg are measurable. In particular, if F is a measurable real valued function, then F plus equals max F0 and F minus equals minus min F0 are measurable. So max Fg, so proof, is nothing but 1/2 of F plus G plus mod F minus G, and min Fg equals 1/2 of F plus G minus mod F minus G. So F and G measurable means F minus G measurable, mod F minus G measurable, F plus G plus mod F minus G measurable, multiply by half it's measurable. So this is measurable. Similarly, min is also measurable. Okay, so remark, F plus is called the positive part of F and F minus equals the negative part of. Note that positive, F plus, F minus are both non-negative functions. F can be written as F plus minus F minus, and mod F is nothing but F plus plus F minus. Now lemma, this kind of thing we have done many times. Okay, so XS measurable space, F real valued measurable function defined on X, then for every E contained in R Borel, F inverse E is Borel. So proof, so set of all S equals set of all E in R, just that F inverse E is Borel. So empty set and R belong to S, and then F inverse of E complement is F inverse of E complement, and F inverse of union I EI equals union I F inverse of EI. From this you get that S is a sigma algebra by measurability. All open sets are in E. We proved this CF corollary, proved earlier. Therefore, open sets are all in S, so implies all open sets are in S, sorry, not in E. Implies all Borel sets are in, and that completes the proof of this theorem. So corollary of this, okay, XS measurable space, F real valued measurable function on X, then F measurable F is a real valued function on X. F measurable if and only if F inverse U belongs to S for every U Borel. Proof. So F measurable, then by lemma F inverse of U is in S for every U Borel. Sorry, it should be belongs to S. Sorry for that. So F inverse of E is in S means okay, so then let us define this as S tilde. So let me do this again. So XS, F is measurable real valued function defined on X. For every E in R Borel, F inverse E belongs to S. So you define S tilde is set of all E in R, F inverse E belongs to S, and then phi and R belong to S tilde. F inverse E complement is F inverse of E complement. F inverse of union EI equals union I F inverse of EI. So S tilde is sigma algebra. By measurability, all open sets are in S tilde. Compare corollary proved earlier. Therefore, all Borel sets are in S tilde. Okay, so this is the lemma. So sorry for the confusion. Okay, so by the lemma F inverse of U is in S for every U Borel. Okay, conversely F inverse U in S for every U Borel implies F inverse of alpha infinity belongs to S for every alpha in R, and then alpha f is real valued, implies f is measurable. Okay, so this proves. So now measurability is seen is nothing but the imitation of continuity. Suppose I have two topological spaces xt and yt dash, then what do you say that f from x to y is continuous? That means f inverse of u open for in x for all u open in y. So similarly for measurability we are saying we have xs measurable space, and then f is a real valued function, and so on R we take the Borel sigma algebra B1, and then inverse image of every Borel set is a measurable set. That is what we are saying. So just like the definition of continuity. In fact, if you have two measurable spaces xs and ys dash, one could talk of f from x to y measurable if f inverse of u is in S for every u in S dash. Okay, so this could be an abstract definition of measurability between abstract measurable spaces, but we are restricting our attention to real valued functions. So for real valued functions, measurability essentially inverse image of every Borel set should be measurable. That is all that we are saying. Okay. Proposition xs measurable space, f measurable real valued function, phi from R to R Borel measurable. Then phi composed with f is measurable on x. So proof. So set of all x in x such that phi composed with f of x is bigger than alpha equals f inverse of phi inverse of alpha plus infinity. Now this being a Borel measurable function is a Borel set, and by the previous lemma this belongs to S because previous corollary, therefore this belongs to S, and that proves the result. So remark, in general composition of measurable functions is not measurable. We will see an example of this, but if you have that the second function is Borel measurable R to R, then the composition is measurable. Okay, so that is the moral of the story. The proposition xs measurable space, fn sequence of extended real valued functions on x, measurable functions. So you take for x in x, you define h of x equals sup over n fn of x, g of x equals inf over n fn of x. So because these are extended real valued, implies h and g are measurable. So let alpha belong to R. So you take set of all x in x such that hx is bigger than alpha. So if the sup is bigger than alpha, there is at least one of them, fn's, will be bigger than alpha. So this is in union n equals 1 to infinity. Set of all x in x, fnx is bigger than alpha, and therefore this belongs to yes. And similarly, set of all x in x, so gx is less than alpha equals union, at least one of them must be less than that. So this x in x, so fnx is less than alpha, and again this belongs to yes, and therefore h and g are measurable. Okay. Corollary: XS measurable space, Fn sequence of real valued measurable functions. Then lim sup n tending to infinity of Fn and lim inf n tending to infinity of Fn are measurable. In particular, if fnx converges to fx for all x in x, then f is measurable. So the limit of measurable functions, convergence pointwise everywhere, is measurable. So proof. So you take Gn equals sup m bigger than or equal to n Fn, this is measurable, and then lim sup Fn n tending to infinity, this is nothing but inf over n Gn, so measurable. Similarly, you take Hn equals inf m bigger than or equal to n Fn is measurable, therefore lim inf Fn n tending to infinity, which is nothing but the sup over all n Hn, this is measurable. Okay, so if Fnx converges to f of x for all x in x, then you have f is nothing but lim sup Fn, which is equal to lim inf Fn, and therefore this implies that f is measurable. Definition: XS measurable space, a simple function on x is a function of the form, we have seen this before, f equals sigma I equals 1 to k alpha I chi of ai, okay, ai measurable sets in x and then alpha I reals. Okay, so we are going to, when we say simple function, it's automatically measurable because of the example where we saw chi of ai is measurable if and only if ai is measurable. Okay, so these simple functions are the building blocks of integration theory. So we will, Lebesgue's integration theory starts with defining the integral on simple functions and then going on to non-negative functions, general functions, and so on. So we have the following very important theorem which you must remember very well. Okay, so theorem, it's a very important theorem. Theorem XS measurable space, F non-negative extended real valued measurable function. Then F is the increasing limit of a sequence of non-negative simple functions. On X. Okay. So we are going to, so every non-negative measurable function which is extended real valued can be written as the increasing limit. That means you can find a sequence fn of x which is monotonic increasing and the limit is f of x. Okay. So proof. N fixed positive integer. So 1 less than equal to I less than equal to n times 2 power n. Define f eni equals f inverse I minus 1 by 2 power n I by 2 power n, and fn equals f inverse n infinity. So what are you doing here? So I am taking 0 and then I am taking n. So whenever x inverse image of n plus infinity is given by fn, and this portion here I am going to divide each subinterval of length 1 by 2 power n. So there are n times 2 power n such intervals, and if f falls in any particular interval here, then I put eni is the inverse image of the f here. So this is how I am defining this thing. So f measurable implies eni, fn are all measurable, and then of course if I define small fn equals n times chi of fn plus sigma I equals 1 to n times 2 power n I minus 1 by 2 power n I minus 1 by 2 power n chi of en. So what am I saying? So in other words, if fx is greater or equal to n, then we say fnx equals n. Okay. If fx is less than n, then there exists a unique I such that I minus 1 by 2 power n is less than or equal to fx is less than I by 2 power n. Okay. And then we are going to put fn of x is equal to I minus 1 by 2 power n. Okay. So if f of x falls after n, then you put this lower value. If it's before n, then it will fall in one of these intervals, and then you take the lower end of that interval to do that. Okay. So this implies of course that fnx is less than or equal to fx for all x. Okay. And this is of course a simple function. Okay. So we just have to show two things, that to show fn is less than or equal to fn plus 1 for all n, and fn increases to f. Okay. So if fx is greater or equal to n plus 1, so this implies that fn plus 1x equals n plus 1, and then fnx, since it's bigger than or equal to n plus 1, is bigger than n, and therefore this is equal to n. So this implies that fnx is less than or equal to fn plus 1x. So if fx n less than fx less than n plus 1, then you have fn plus 1 equal to I minus 1 by 2 to the n plus 1 for some I such that fx belongs to I minus 1 by 2 to the n plus 1, I by 2 to the n plus 1, which will be contained in n plus 1. Okay, because we are going to divide like that. And now further, and fn of x will still be n, and therefore this implies that fnx is less than or equal to fn plus 1x. Now finally, if fx is less than n, then there exists an I which is less than or equal to n 2 power n, such that fx belongs to I minus 1 by 2 power n, I by 2 power n. But this is also equal to 2 times I minus 1 by 2 power n plus 1, 2i by 2 to the n plus 1. So what is fnx? Fnx is I minus 1 by 2 power n. What is fn plus 1 of x? Now this interval here can be written as 2i minus 2 by 2 to the n plus 1, 2i minus 1 by 2 to the n plus 1, union 2i minus 1 by 2 to the n plus 1, 2i by 2 to the n plus 1. So fn plus 1x equal to either, if it falls in this interval, it is 2i minus 2 by 2 to the n plus 1, which is I minus 1 by 2 power n, which is fnx, or it can be 2i minus 1 by 2 to the n plus 1, which is bigger than I minus 1 by 2 power equals fnx. Therefore, for all x, we have fnx is less than or equal to fn plus 1 of x. So this is a monotonically increasing sequence. So now if fx equals plus infinity, this implies that fnx equal to n for all n, and so fnx increases to fx. If fx is strictly less than plus infinity, there exists a positive integer n such that fx is strictly less than n. Then for all n greater or equal to capital N, by construction, you have that fx minus fnx, which is the same as mod fx minus fnx, because this is non-negative, is less than 1 by 2 power n. Because you see, it's in this interval. If f falls in this interval, you are putting the lower end point as a value as fn. So the distance between fx and fnx is always less than 1 by 2 power n in this case, and therefore this implies that fnx increases to f of x. So this proves the theorem, very important theorem. So every non-negative measurable function is the increasing limit of non-negative simple functions. Okay, corollary, xs measurable space, f real valued measurable function, then f is the limit of simple functions. So you write proof f equals f plus minus f minus. Because it's real valued, you don't have ambiguity in the definition. Both of these can't be infinity, and therefore this is well defined. And now you take phi n simple, 0 less than or equal to psi n simple, phi n increases to f plus, psi n increases to f minus. Therefore you have that fn minus phi n minus psi n tends to f plus minus f minus equals f, and then phi n minus psi n is simple. Okay, so that proves this corollary. Okay, so this completes the fundamental properties of measurable functions. Next time we will take up a very particular case of a function called the Cantor function, which is like the Cantor set, the Cantor function. They are closely related anyway. They are an immeasurable source of counterexamples.